Hello everyone, my name is Bernardo Patella. I'm an assistant professor at the University of Palermo in Italy, and I'm glad to show you part of our research that concern the reduction of graphene oxide supported on paper using a carbon dioxide laser and its application as a chemical sensor for phosphate ions. So first of all, we should say why it's important to monitor phosphate ions. It has two main goals. The first one is to monitor the environmental pollution. Indeed, phosphate and phosphorus in general, it can be used, is highly used as fertilizers, and its overuse led to its release in water, and its release causes different problems, such as microbial growth damaging. It limits the nitrogen fixation, and moreover, it is cause of a very important phenomena called eutrophication. Due to this phenomena, there is the overgrowth of algae that leads to different problems, such as it decreases the amount of dissolved oxygen in water, and it also avoids sunlight to goes inside the body of water, and it of course creates problems for the aquatic life. For human health, there is a certain amount of phosphorus that is must be found in blood that goes from 2.5 to 5 milligram per deciliter of blood. And if we have levels of phosphorus higher or lower of this value, we have two different diseases called hyperphosphatemia and hypophosphatemia. And all those two diseases leads to different problems such as bone and teeth fragility, kidney damage, heart attack, and it causes strokes, for example. For all of these reasons, the United States Environmental Protection Agency, the US EPA, has set different limits for phosphate ions in water, depending on the kind of water. So we have different limits from 1 to 0.26 micromolar, depending on the water, for 1 micromolar for the water that doesn't go into reservoirs, while we have a limit of 0.26 micromolar for water within reservoirs. So it is, from this perspective, it is very important to find a method that can quantify phosphate ions in an easy way and in a fast and a cheap way. Nowadays, phosphate ions are quantified using a colorimetric assay called phosphomolybdate blue spectrometry. In this method, phosphate ions react with molybdate ions, producing a compound that is called is a kegging ion of phosphorus. These kegging ions can be reduced using chemicals such as for ascorbic acid to produce a compound that has a blue intensity, and thus the intensity of this solution, the blue intensity of this solution can be quantified to quantify phosphate ions. This method is for sure sensitive and selective, being a spectrometry method. I have a very low limit of detection in the micromolar range, that is the range that we need to find out, but it has different drawbacks that are problems related with spectrometry, because it is not cheap, it is not friendly to use, it is definitely not a fast analysis, and cannot be carried out in an in situ or real-time way. So in this work, we are trying to develop a chemical sensor for phosphate ions, because that chemical sensors use a very low power consumption, are really easy to use, so our use friendliness, can be miniaturized using also nano materials, and from moreover, due to their electrical output, can be fabricated to be to carry out online in real time and in situ analysis. As proof of that, even the Environmental Protection Agency suggested to develop new electrochemical sensors for the different application. One of these applications in this work was to produce a sensor for phosphate ions. The problem of phosphate ions, from an electrochemical point of view, is that they are not active, so they cannot be reduced or oxidized. So in this work, we have still used the molybdate blue reaction. So we have made react phosphate ions with molybdate, and then we have reduced the kegging ions using electrochemistry. So we have used an electrode made of graphene oxide, a reduced graphene oxide, supported on paper. Now I will say why we choose a paper. So the experimental started from a standard Batman paper. It has been filtered with different amount of graphene oxide, and then using a carbon dioxide laser, it has been reduced back to graphene. This is a very important aspect of this work, because simply by tuning the parameter of the laser in terms of speed and power, it is possible to obtain different kind of electrodes. Here, for example, in the image B, C, and D, I show the morphological image of the electrode reduced using a too fast or a too powerful laser, and using the optimized parameters of the laser. As we can see, there is a different morphology because the laser parameters changes. In this work, we have developed the sensor supported on paper, and the final electrode is shown in the figure A here. But simply by changing the supporting the support, we can make sensor in different supports, such as band-aid or textile. So this technique is very, very versatile. So we have fully characterized the electrode. As we can see, in figure A shows the same image of the electrode. This line is the reduced part of the graphene oxide, while on the left, on the right side of this line, there is the unreduced graphene. And as it's possible to see, there is a very different morphology and in the reduced part, there is a very high, is a very rough surface. So then we have tried to understand how much graphene oxide we had to put on top of the paper. So we have studied the effect of this parameter on the electrode conductivity. And as it's possible to see, the higher is the amount of filtered graphene oxide, the higher is the conductivity of the electrode. But by filtering 20 ml of solution, we have found the best conductivity, and we didn't exploit higher amount of graphene oxide simply because the filtration process then takes too long, more than 5 hours. So we have stopped to this amount. After this optimization, we have studied the effect of scanning speed, laser scanning speed, and laser power showed in image C and D. And as it's possible to see, these two parameters have a very high impact on the electrode conductivity. And particularly in the case of scanning speed, we have we need scanning speed that are not too fast, but not too slow, because then the support would be burned. And the optimum scanning speed was found to be 75 millimeters per second. In terms of laser power, we have a plateau in the laser power between 1.8 and 1.9 watt, and we have chosen this parameter, 1.85 watt, as the optimum one. The electron has been then characterized, physico-chemically characterized, and we have carried out ADS, XRD, and Raman analysis in order to find out the degree of reduction of graphene oxide. As it's possible to see from the ADS analysis, ADS analysis after the reduction of graphene oxide shows a much higher peak for carbon and lower peak for oxygen, demonstrating that the electrode has been reduced. And the same result were given by the XRD and the Raman spectrum, but with all those analyses, we were not able to find out the degree of reduction. So in order to find out this degree, we have carried out XPS analysis before and after reduction. And as it's possible to see, for example, for the C1s spectrum, before and after reduction, there is a total disappearance of the carbon and oxygen bonds, such as COC or OCO. So demonstrating that the electrode has been fully reduced, and using even the oxygen peak, we have found that after the reduction, the oxygen over carbon ratio decreases of 63%. So we have obtained an electrode, a graphene oxide, reduced graphene oxide electrode, with a degree of reduction of about 60%. This is a very high result using a very cheap and easy protocol. So from an electrochemical point of view, this electrode has been then used as an electrochemical sensor for phosphate ions using the phosphomolybdate blue reaction method. The electrochemical technique was chosen to be cyclic voltammetry from minus 0.5 to plus 1.5 volts using a scan rate of 10 millivolts per second. We have optimized the concentration of molybdenate ions, the solution pH, and the supporting electrolyte. And then we have calibrated the electrode, and we have carried out selectivity test and real sample analysis. And more important, are ready-to-use application. That is the final goal of this work. So here we show the detection mechanism. In the A image, we can see the cyclic voltammetry using just sulfuric acid, and it's possible to see there is no peak related to oxidation or reduction of the electrode. The same was obtained adding molybdenate ions, so there is no reactions occurring using sulfuric acid and molybdenate ions. But when phosphate ions are added to sulfuric acid and molybdenate ions, three well-defined peak appears related to the oxidation and reduction of the kegging ions of phosphate. By giving a look to the literature, we can see that these kegging ions has two isomers, the alpha and beta isomers, that can be oxidized and reduced at different potential that are you can find in the table. Increasing the concentration of phosphate ions, as you can see, the peak of oxidation and reduction of kegging ions increases linearly. So we find out that the current density increased linearly with phosphate concentration in two linear ranges from 0 to 20 macromolar and from 20 to 100 macromolar. A plateau was reached for phosphate ions concentration higher than 1 millimolar because molybdenate ions is fixed, the concentration is fixed to be 0.1 millimolar. Thus, it starts to act at higher concentration of phosphate ions, it starts to act as a limiting reagent. The electrode reproducibility was calculated to be 7.2% using three different electrodes, and the limit of detection was calculated to be 0.4 micromolar. So in line with the US Environmental Protection Agency limit set that I discussed before. So then we have carried out selectivity tests simply by adding to the solution different chemicals such as nitrates, iodide, chloride, potassium silicate, iodide, heavy metals, and nitrite. And as it's possible to see from this image, the peak current density ratio is still fluctuating over the 7.2% error that I discussed before, except for nitrate ions. So we have a kind of effect of these ions on the detection of phosphate ions, but we are still trying to understand why there is this interference. But it's important to say that this experiment was carried out using a very high concentration of interfering agents, particularly 10 times higher compared to the phosphate concentration. So it is very unlikely to find a real water sample that have so high concentration of nitrate ions. So then we have collected a real water sample from Palermo, a river water from Palermo, and it was tested without any physical pretreatment. Then the standard addition method was carried out after its acidification and addition of ammonium molybdate. And using our sensor, we found out a concentration of 3.8 micromolar of phosphate ions in this water. But in order to back compare our result with a standard technique, we have carried out a colorimetric assay using the standard colorimetric assay with the phosphomolybdenum blue reaction, and we found out a concentration of 4.4 micromolar. So the two sensors are gave the same result, 3.8 and 4.4 micromolar, so suggesting that our sensor gave results very, very close to the standard technique. So it can be used as a real alternative to this analysis. But as I said, here we still added the reagents, still added phosphate, molybdenate ions, and sulfuric acid. And so we cannot carry out any kind of real-time or in-situ analysis. So then we have carried out ready-to-use electrochemical sensors. And this is why we choose paper as substrate. Indeed, we have tried to see if paper could be preloaded with sulfuric acid and molybdenate ions in order to be released then in the water to be analyzed, in order to make an analysis without adding any reagents. So we have studied the release of sulfuric acid and molybdenate ions in DI water, particularly 10 microliters of sulfuric acid and ammonium molybdate were let dry on the paper. And after it's drying, the electrode was immersed in 1 ml of DI water, and the release of pH was studied using a standard pH meter. And as it's possible to see from the A image, the solution pH reached a plateau after 3 minutes, and using a solution of 0.75 molar of sulfuric acid led to a final pH of 1.7, that is the one that we want to quantify molybdate, to quantify phosphate ions. A similar approach was made to understand how much molybdate ions we had to let absorb on the paper, and we found out that 3.77 of millimolar of molybdate ions are enough to release 0.1 millimolar in 1 ml of the water. So this experiment clearly demonstrated the ability of the proposed sensors to absorb the required chemicals and to quantify phosphate ions without the need to add any reagents to the solution. So concluding, a paper-based sensor has been fabricated for the detection of phosphate ions in water. Graphene oxide was successfully deposited and reduced on different substrates such as paper, band-aid, or textile. A true electrode system was successfully fabricated by simple filtration and carbon dioxide laser reduction. The fabrication method is cheap and highly reproducible, and the detection procedure is simple and rapid. And the proposed sensor can detect phosphate ions with high sensitivity and low limit of detection, with excellent stability and selectivity. And paper-based reduced graphene oxide sensor were successfully tested with real samples, providing their applicability. And the presence of paper substrate was used to preload the sensor with all the chemicals and to quantify phosphate ions without any sample pretreatment. So enabling in real time and in situ analysis. So here I conclude my presentation. Thank you for your attention. And if you have any question, please don't hesitate to ask.